Good morning, professors and guests. We are Team Agora, and our project title is Decentralized Crowd-curated Discussion Platform. Now let's jump into what it is. So first of all, why did we develop this crowd-curated discussion platform? Well, we looked at the current state of social media platforms, and especially we noticed that these days social media platforms are increasingly more important when it comes to letting people know the latest news and information. But there's a huge flaw in that these social media platforms are often controlled by like a single company or a single entity. And this represents a single point of failure. So as you can see in this diagram here, this is what a typical social media platform would look like. There's a bunch of huge server farms somewhere, users connect to it, and they're all controlled by one company. And this means that these platforms are susceptible to censorship and manipulation. So you could have manipulation due to numerous factors. So it could be the government pressure, it could be pressure from shareholders, maybe they have a political leaning of their own, or it could just be like employee misbehavior. And the last problem is that most social media platforms don't really allow you to be anonymous and have an identity. They all require you to have public profiles. So with Agora, which is our decentralized crowd-curated discussion platform, we wanted to take a step back and just rethink the whole architecture. So instead of having like company-owned servers, every user basically runs a node, and the entire network or platform is just made up of nodes connecting to one another. And this means that there is no single point of failure. So you could have 100, 200 nodes and maybe like 10 or 20 get knocked out, but the platform still keeps going on. And lastly, it also means that instead of being controlled by like a single entity, which can be subject to manipulation or attacks, it's controlled by the users, and it's very democratic in that usually like the majority wins. And here I just wanted to give a few examples of how our features compare to existing social media platforms. So for content distribution, websites like Facebook or Twitter, they usually use commercial CDNs like Kamai or something else to get the content from their servers or the platform to the user's computer. For Agora, we chose to use peer-to-peer technologies so that every node in the network can contribute to distributing content as well as consuming content. And we use IPFS, which Long will explore later in the presentation. So next is content prioritization. In existing social media platforms, we have important features such as newsfeed or front page or the feed, where users are shown content that they're most likely to be interested in. And these are usually run by recommender systems powered by big data. But since our entire platform is decentralized, it's not really feasible to ingest all the data of the network and get all the required compute capacity in order to run like machine learning algorithms to recommend stuff to every single user. Instead, we came up with this concept called crowd curation, which Houghton will explain more in detail. Next, we have freedom. So in existing social media platforms, you sign up, you basically agree to like a whole list of terms and conditions, and it's also closed source, so at the end of the day, you're just signing up for whatever they give you. And another example is, let's say you open up your newsfeed and you see like 5 or 6 posts. You can't really tell or intuit like why the posts appeared there in that order. It's completely up to the platform themselves. You have no transparency. Whereas with Agora, we wanted to make it as transparent as possible, so you can actually see like why the posts came up in this order, or why these posts came up on your friend's computer but not on your computer. And last but not least, it's also extensible. It's open source. We try to make it as modular as possible so people could maybe swap it out or develop new things on top of it. And lastly, we also have the privacy factor. So as I mentioned earlier, existing social media platforms require public profiles. but we decided to go for cryptographically verifiable identities instead, in order to allow users to be anonymous, but at the same time authenticate that they're talking to the right person. So, to sum up, our objectives are to create a decentralized social media platform with decentralized crowd curation. And our next objective is also to be resistant against attackers, be it like attackers trying to flood the network with spam, or maybe even hackers. So those are our objectives. And now I shall pass over to Long, who will explain more about the system architecture.
Okay, thank you, Prashant, for the intro. So I'm going to talk about how we actually implemented the things. And Prashant mentioned two important things. One is the decentralized platform, and second is crowd curation. In the following, I will talk about the first thing, the decentralized platform. So what do we mean with decentralized? Instead of having a traditional client-server architecture, we are actually approaching this problem with a peer-to-peer network. Here's a very simple example of a peer-to-peer network, and you see computers here, where we call them node, and how it works, and how do they retrieve and distribute data is by connecting directly peer-to-peer to other nodes. And in this peer-to-peer setup, in this decentralized setup, we need to rethink a few things. One thing is there's no central data storage. The data needs to be shared among the users. And the second thing is there is no such concept as a central authority to give you identities. So there's nothing like a Facebook sign-up page. So these are the things we need to rethink of. So, okay, how about data distribution and storage? What we use is called IPFS. It's the Interplanetary File System from the Stanford Protocol Labs. And IPFS is a peer-to-peer distributed file system. So how you can imagine this is you have one single file system which is shared and abstracted, but the data is actually stored in a peer-to-peer network, in a swarm of nodes. And this is very this technology is still quite in its infancy, so we had quite some problems in the beginning to start working with it. But we choose to use it because it gives us a complete solution to deal with data persistency in a peer-to-peer network. In addition to that, we use libp2p, and we use that to directly connect nodes together. And libp2p is quite neat because it takes care of a lot of things such as net traversal, so we don't need to worry about that. So this is how our data flow looks like. And on the left, we see here it's the connection manager. This uses libp2p, as I just described, to connect to our Agora nodes directly. So what it does is it requests new content from our nodes, and what it receives are file names. So these file names are used by the data manager to directly retrieve it from the IPFS system. On top of the entire system, we have the content manager, which kind of supervises the entire process and also stores metadata such as, this content, where did it got it from? Yeah. So that was our data storage system. And the second thing we needed to rethink was our identity system. So instead of having a centralized identity creation, we use cryptographic identity creation. So it's basically just a private public key, which every computer can generate by themselves without any authority to check. And they use the public key as their identity, and the private key is kept secret and is used to basically prove that you are in control of that identity. And I mean, this is nothing new. What we have thought about this, but what we use in our system is actually two types of identities. One type is for the node, the computer itself, and one type is for the author identity. So why did we choose to split? Why do you need two identities? So the reason is that you as an author, you might want to change your device. So, or you might even want to use multiple devices to interact with the Agora network. So it's much more flexible if you can separate those two. Yeah. So during our implementations, we face some challenges, and I want to feature two things and tell you how we basically solve them. And the first one is data integrity. So as I said before, all the data is shared among the users. So we need to stop them or we need to prevent them from actually manipulating the data, because the data is they have access to it. The second thing is peer churn, and peer churn is peculiar to peer-to-peer networks. What peer churn is that basically you have nodes which randomly go online and offline, and this can really affect the network. Because imagine I have the laptop right now. If I close it and walk away, the data which is initially provided by that laptop is suddenly not available. So yeah, so for data integrity, we basically have two mechanisms to ensure it. First is we call it verifiable authenticity. For this one, remember we had an author identity. The author identity is used to create a digital signature. So with that signature, everybody in the network can verify if the signature is valid or not, but only the author can actually create the signature. And second is that we enforce strict immutability. It means you cannot change content as soon as you insert it into the system. And we're using property of IPFS. Like IPFS is storing things content addressed. What means content addressed? Like in a traditional way, you usually address things location based. So you have an IP or a file location. But in IPFS, the address is defined by the content itself. So when you change the content, if you flip only a single bit, the hash, the file name, will basically change, and it's basically a different file. Yeah. And last thing is peer churn. So peer churn, obviously, the solution is to create data redundancy, and we've done that by creating a special kind of content distribution, and we tested our peer churn in the following setting. So we have the feeder node, which basically feeds the network with content, and we have the reader node, which tries to read from the content. But the catch is the feeder and the reader are not directly connected. So in between we have three intermediate nodes, which are unreliable. So what we said basically that they are only online for about 50% of the time. So now we measure over time how much content, how many posts got fed into the network, and how many actually reach the reader. And you can see, of course, on this level is where all three intermediates are offline, and you can see that it kind of levels here. But as soon as as soon as one of them come up again, we can quickly regain the content we just lose. So we actually are quite near to the number of values, the number of content we inserted, and the number of contents we received. And I want to point out in this case that this is an extreme case. In the Agora setting, we assume to have much more nodes than just 3, and much more nodes which are not going offline and online that quickly in an interval. So this gap could be actually much smaller, but we wanted to test it in a like extreme case. Okay, so that's it for the decentralized platform. I want to hand over, and Horton is going to talk about what I think is a quite new concept. This is the cloud creation.
Yeah, thank you. So I'd like to introduce crowd creation by giving you an understanding of what kind of problem we're trying to solve. So this problem is something that I like to call the problem of moderation. In other words, how do you allow users to see content that they want to see? And in a centralized setting, this is really easy. So for example, in Facebook, when a user connects, Facebook has a profile of the user that is generated using machine learning or recommender systems, and it can just selectively provide data to the user. However, this doesn't translate very well to the Agora network, and the reason is because of our node architecture. Rather than having one central server managed by a single authority, we have many, many different nodes that you can pull content from. And therefore, even if one particular node changes the way your content is viewed, you can still get content from other nodes. And so this type of structure doesn't quite work. So in order to create something that's similar to what Facebook provides, we made two key observations. The first observation is that nodes can choose what content to send to other nodes. So you can provide any type of criteria here to select the type of content that you share with other users of the network. And secondly, you can choose which nodes to pull content from. So you can ask specific nodes for content, and you can choose these. So by applying these two key observations, we can create something known as crowd curation. So using the first observation, if we naively assume that every node has some sort of filtering system that can just filter away undesirable content, we have this model. And in this case, the spam filter is created using machine learning. So here you have attackers that are sending spam into the Agora network, and this is curated using multiple layers of nodes. So you can see that the original spam data is slowly mitigated until there is little to none left after multiple stages of filtering. However, there's a fundamental error or a fundamental flaw in this model, which is that we are assuming that every spam filter is really effective. However, this isn't necessarily the case. You can have nodes with very ineffective spam filters that pass through all the data, and this can cause the network to become really congested with spam, especially if the majority of users have weak spam filters. So here we apply our second observation. Nodes can choose what nodes to pull content from. And that means that users can choose to pull content only from nodes with good spam filters. And so here is an application of that. Here you can see our full crowd curation algorithm at work. You can see that the 3 spam nodes are spamming this fully connected Agora network. And slowly but surely, the legitimate users, the non-spammers that are denoted in green, separate from the spammers completely after a short period of time. And this means that these two networks no longer interact. And therefore, these legitimate users will see only content that they like, and these users will see content that will not be able to influence this network anymore. And so I want to point out that I use the word spam, but the word spam in this case is relative. So for example, in this case you can see that there's a spam network and a non-spam network, but these could just represent people with different viewpoints. And perhaps these individuals don't want to see posts from these individuals. And the crowd curation algorithm works similarly and separates these groups automatically. And this is just simply using local filtering and a very simple blacklist system to be accomplished. And so we evaluated the effectiveness of this algorithm over time. You can see that once the nodes are blacklisted, so here you have a 3-node setting. So rather than a complicated multi-node setting, we just have 3 very simple nodes. One is a spam node and 2 legitimate nodes. And once the spam node is blocked, you can see that the spam ratio, or the ratio of spam posts to legitimate posts, decreases asymptotically to 0. And so you can see that our crowd curation algorithm is really effective even in the worst case when the network is really small. So now I'll be talking to you about the limitations of the Agora network that we just proposed. So we have 3 key limitations. The first limitation is content length. So unfortunately, due to the way that Agora works, each node is actually run by a user, possibly on a home connection. And so the bandwidth requirements of Agora need to be quite small in order for for as many users as possible to participate in the network. And so the content length cannot be too large, because if the content is spread to multiple users, then the bandwidth requirements will be multiplied. Secondly is network size. As I mentioned before, algorithms such as crowd curation and pure churn mitigation, these algorithms only work when there's a large number of nodes, and although they function somewhat in smaller instances, they are not as effective. And finally is the issue of timestamps. What I mean by timestamps is the timestamp on a post or comment that denotes when the user posted it. And this is actually not checked by Agora because it's very difficult to do. And what this means is that a timestamp cannot be verified to be completely accurate. Of course, if a user postdates their posts, it's very easy to verify by comparing to the current time. But nothing stops a user from posting posts in the past. And so this allows a falsification of history attack. However, as long as users know not to trust data that is too old, this won't pose too much of an issue. However, this does impose a burden of knowledge on the user, and so this is something that we need to work. So now we're going to be doing the demo. So the demo is a demo of the crowd curation at work, as I demonstrated in the full crowd curation slide. So we can see a live network separating into two as the crowd curation algorithm is running. So here you can see that there are some spam nodes. These are denoted by the borders. So these are spam nodes because the borders are red, and these are legitimate nodes because the border is green. And you can see that the slow evolution of the network topology as the nodes are being blacklisted and the spam network is slowly separating from the non-spam network. So as I mentioned before, these could actually be just groups of people with different viewpoints. And so one concern could be that this architecture could form an echo chamber. So you can have like users that just all agree with each other, and you have users that just don't agree with each other and they never interact. And this is actually by design. If a user wants to participate in an echo chamber, Agora is not going to say no. But at the same time, if you are aware of echo chambers and you want to avoid them, actually Agora is going to fit you with like-minded individuals through crowd curation organically. And so if you don't desire to see an echo chamber, Agora will actually not give you an echo chamber. Whereas if you're a user that just wants to see people that agree with you, an echo chamber will form and you will see only posts that agree with you. So in essence, Agora is going to give you the content that you want and won't impose any a particular agenda on you. So here's the network running at the moment. You can see the edges disappear, and the edges disappear as the blacklisting occurs. So here you can see the data as it's running live here. You can see the spam ratio updating as the content in the network is propagating. The reason why it's not really fast is because we modified the algorithm so that each node only pulls from a random number of nodes it connects to. So for example, this node only has 1/6 of the chance to pull from a spam node, which is why this link is still online. Whereas in the beginning, you can see that a lot of content. Yeah. So here you can see that the network is fully separated, which proves that our content curation algorithm works perfectly. Right. So wrap up. For the Agora project, we set out to accomplish 3 goals. The first goal is decentralized identity creation. And we accomplished this using our 2 identity system that Long described. The second thing that we set out to do was create a social media network that was decentralized and had content directly shared between users. And we did this by building a platform on top of IPFS that allowed computers to just connect with each other and share posts with each other. And finally, we wanted users of the system to be able to see what they want to see. And so the crowd curation system is a revolutionary idea that implements this functionality. So some future improvements of the project, we can do content scoring. So right now, one possibly less desirable thing in our system is sorting, because sorting currently is done by just simply sorting by descending order of timestamps. So anything that is new will be at the top, and everything that is old will be at the bottom, and all the spam content is just hidden. So content scoring would be to have a separate machine learning algorithm that functions as a recommender system, and it can score each content based on how likely it is you will like it. And unfortunately, it's also really complicated to implement, so this could be an FYP all in itself. The second thing is we plan on extending this project so it works on mobile devices. Some challenges with mobile devices are, number one, the bandwidth requirements are even more limited, and secondly, running a full node on a mobile system is not feasible because background processes in mobile operating systems are frequently killed, and Agora isn't designed to handle being killed a lot. So thank you for listening. You can see the code on GitHub right now. It's on github.com/turbotardigrade. Thank you for listening.
Thank you.
We will now take questions.
Okay, I have a few questions. So the data manager, it's on one node, is that right?
Yeah, and each node has a data manager.
Oh, sorry, each node has a data
Yeah, this is the architecture for one node.
I see, I see.
So the entire so actually there is no feature of Agora that spans multiple nodes. All features of Agora that we've described are always local, and that's because you can't guarantee that other nodes are trustworthy.
Yeah. Okay, that was the point. Okay. Who makes the blacklist for your spam?
So actually, the blacklist is also local, and it's determined by the content that you get from peers. So when you pull content from a node, you can check how much of it is spam, and it's checked automatically by the spam filter or the machine learning algorithm. So the machine learning algorithm will run a very simple classification algorithm. In our case, we used a very simple naive Bayes classifier, which is proven to be fairly effective at countering spam. And it will either label it as spam or not spam, and we can calculate the ratios of the content that this node provides. And if the ratio is too high, we simply blacklist it. However, we make sure that each node will connect to at least a few nodes. So the network is sparsely connected, but there won't be a node that just blacklists everything, and so no content can be seen.
Okay, that classification is based on what data?
The classification data is based on actually users using the platform. So a user, when he uses the platform, he can mark things as spam, and that will train the algorithm.
So the signal comes from the user that this item is spam.
Mm-hmm. And the machine learning algorithm will simply learn the preferences of the user as the user normally interacts with the platform.
The only problem is, let's say it was a Trump supporter and someone who doesn't like Trump, something like that. I mean, if you didn't like Trump, you could say, I don't like this. Trump is great, so I would label it as spam. Isn't that not spam?
So actually, the definition of spam in our architecture is actually just undesirable content. If you don't want to see it, then the spam filter can get rid of it.
So you're using standard spam filter,
yes,
right?
yes.
So you basically cannot modify what David was suggesting, right?
Oh, you can. Because our content curation, you can swap out the content curation algorithm to whatever algorithm you want. It's just that our particular implementation does this. And actually it's quite desirable because a user that's like a pro-Trump supporter will not read anti-Trump supporter messages. Or at least he doesn't, a pro-Trump supporter might not want to see anti-Trump supporter posts.
No, from technical standpoint, that doesn't matter. It's not a concern. It's basically it provides flexibility and option to modify what you're filtering.
So essentially, if you want to see it, you will see it, and if you don't want to see it, it will be filtered.
Yeah, I think one additional one I would make here is actually the creation model is pretty pluggable. So you can see here that the creation model actually interacts with the content manager. And we're providing an interface here, which you can easily swap. And the idea is basically, we are providing an open source peer-to-peer solution. And we want to provide it that people can choose what they want to use. We are not, because that's exactly what we want to achieve, that people can don't have one option of, I have to follow what Facebook is giving me. But instead they can actually choose themselves. So alternatively, instead of a machine learning algorithm, you can have something like a trust system, so that you can say, I only pull from exactly those nodes. And whatever they give me, I will read it. Or you can have something like a more randomized one. So I want to have very, very broad spectrum of content. Just give me a random selection. Yeah.
For each node, they'll receive a series of messages, perhaps. Will the order of those messages be the same for each node?
No.
No.
It really depends how it propagates.
Yeah. If you receive the same messages,
the time.
If you receive the same messages, they will be sorted in the same way because the timestamp is actually part of the message. But it's unlikely that two nodes will actually receive exactly the same messages, just because of how the network is structured.
I think to clarify here, the sorting is done locally. So when you want to see the content, this is how you see it. Like for example, if you see you have 100 new posts or something, you might not see all of them. So how do you?
Yeah. So you order it just based on a user can define an order, but our default ordering is just by timestamp. So the ordering will be the same as long as you follow that order.
I see.
Yeah.
So there shouldn't be, for example, any missing messages. That shouldn't happen as such. I mean, absent, accidentally deleted in some way. That should not happen in the system.
So what we do is basically it's like linear. Maybe so when we have a post, we know like let's say this is a post, and you have comments and answers on comments. So what we ensure is that we ensure that all messages upstream are there, because you don't want to have this post, you have a comment and an answer of a comment, but the thing in between is missing. What we don't guarantee is that you get this, because we simply don't know. We need to wait until we get it. But as soon as we get one of them, we can follow upstream, like who is your parent, get that, who is your parent, get that.
Yeah. Okay. Yeah. So we guarantee that chains of messages, the chain will be preserved, but we don't guarantee that all messages will reach every node in the network.
Yeah. So like it can be that although this one answers on this post, it might not be received. But what we guarantee is that your conversations are consistent.
Let me answer two questions.
Yes.
I just don't get it. I think it's completely wrong. To tell you the truth. First of all, each node processes no coding, right? In a distributed manner, right? So you do filter, hopefully you get all lists of messages with timestamps that you based on your local decided choice or desirable choice, you do filtering, right? So my first choice is this is a peer-to-peer. I have two questions. First, this is peer-to-peer. It works for large scale, which I was working on that for 10 years ago, maybe 15. But the thing is, tell me, where do you put content? I mean, Facebook, they have sophisticated algorithms to handle the large scale. Now let's say I have 1 million users in this system. 1 million users, some work, some connected, some not. That's the nature of peer-to-peer, right? How do you connect to which node for content?
So maybe what you imagine is this. You have the mesh network. That's what you might imagine because that's what usually people imagine when.
Sure.
But we're talking of decentralized.
No, peer-to-peer is decentralized. Sure, I'm just saying.
So actually, it functions rather than functioning as like a mesh network, it functions like a BitTorrent network. So
yeah, BitTorrent is still you got a few neighbor propagates to neighbors eventually.
Yes, exactly. So
right,
actually, this functions very similarly. You just choose to connect to the nodes that you want.
But then I'm saying is, then the message you are getting is extremely restricted. Means essentially you cannot compare with with a centralized social media network because essentially you're talking to your neighbor, you're talking to the selected people who you have mutual interests or whatever prior establishment. So that's what I'm saying. It's a completely different system, which is totally wrong to compare with a large social media network because the information feeding you pull from is extremely limited. It's not only by bandwidth, it's basically by nature of the application, it's by your design.
So I think one of the reasons for that is their original concept, which was basically you have a like North Korea dictatorship, and then it's like a sub-network which they can't track. That was their original kind of thinking going back a year.
So this
isn't
actually
sense. It's not trying to compete.
Yeah, it's not actually a replacement for decentralized.
I like that idea. I don't have no objection with that idea. You selected certain things, whatever your target interest is, right? But the thing is, in peer-to-peer, I'm a networking person. Consider for the nature of how do you establish from connection to which node you're going to pull that because you don't know who has that information.
Yeah.
So essentially, you are talking to a few fixed neighbor. Even with BitTorrent, you basically migrate to a very few neighbor in a very slow fashion. So you talk about Korea and then news out there on the internet. You don't actually. The fundamental problem of this is you don't know who has it.
Yeah.
Yes.
True. That's my first question. You sincerely don't know. You're not going to solve that problem because that's a fundamental problem of a peer-to-peer network. It's not your system flaw or anything. It's the nature of the peer-to-peer, which because centralized versus decentralized, that's what it is. Yeah. Because it's number one difficulty is you don't know who has it. Yeah. So that's what I'm saying. This will.
It's not designed to see. It's not designed to allow you to see all content. It's just allowing you to see content that you like.
So no. That's why I disagree with that statement. It doesn't allow you to see the content you like. It's only allow you to see the content from a fixed neighborhood. That's peer-to-peer tell you, right? Because that's the node you're getting content from. It's not allow you to get. That's what I think there is something.
Yeah, but
I like the content says, as David said, I like the content says concern North Korea, particularly incident. But you are not getting that because you don't know who has it. You're only able to pull this knowledge from a few nodes in the peer-to-peer connection.
But the content will traverse around the network because other nodes are also pulling the same content from you.
Sure. But I'm saying consider.
Yeah. But we can't guarantee, of course, that you see all of the.
I'm not going to argue with you, but if if you in my field of research for the pure peer-to-peer, I'm not in the content, I'm not in the crowd resourcing, I'm in the peer-to-peer. This propagate after a few rounds and with live news, and which basically essentially not gonna be working like that, and only centralized which does that. So I'm saying is that there is a major limitation by the architecture because you're using peer-to-peer. It's not because your system. That's
We
my
actually
point.
addressed it in our final report. It's basically that it's also a thing we do not focus on. Like for example,
Well, second,
So it's not designed for
like.
like real-time news. That's not really something that we're
It's just I we can take it offline. I mean, it's just this peer-to-peer architecture going to limit. I'm saying it's not going to help you to achieve what you try to achieve here. Let's go back to the first slide. Your objective. I have a very I don't want to run too long. I have very very quick comments on that. I think you should. I just make a comment. I want to. Some of the things you listed, like social media has problems, this and that. And I think you should think about carefully. Some of those problems cannot be solved by so-called decentralized, which decentralized actually create new problem for you. And some of the things which can be actually worked on the centralized platform, which has nothing to do with whether it's distributed or not, like privacy, freedom, or those. Has nothing to do with whether this is decentralized or not, whether it's transparent or extensible or not. There are elements of refinement and other which are very valid points you're raising. But I'm just saying I want to make a comment. It seems to me that you are a little bit somehow thinking decentralized is the solution for all of those.
No.
Those are not.
Yeah. So we're not aiming to replace centralized technologies. We're proposing like an alternative that could be developed. And
it will be difficult. Let me tell
Yeah.
you. I can even say it's impossible for peer-to-peer to deliver that.
Exactly.
To deliver that.
That's not. If you look at our goals, we never aim to.
But what you're saying is interesting in a sense. This works for a small scale. Yeah, hundreds. I would imagine. You look at the picture you're showing. It takes quite some time to converge. That's only like 9 nodes.
Yeah. The big reason being that the network is not actually designed to be that fully connected. Yeah, it's actually designed to be very sparsely connected. So yeah.
No, you don't have to answer that. I'm just making comments.
Yeah.
You don't have to argue with me. I'm saying that's the 9 nodes, but if this you imagine for peer-to-peer, it's work typically in several million nodes, which going to take if that's the speed of convergence, that thing going to take 1 or 2 days to converge. For that kind of algorithm, work on 9 nodes, take like half a minute. If that's the case, let's say even hours, then for content distribution would not be very, very feasible. That's just a comment I'm saying. It's very difficult to scale.
I guess it's something that we can look at and evaluate more in the future. Yeah.
That's not
Yeah, because we don't have we haven't exactly tested that, so we can't really give you comments on that.
may I?
Yeah, sure.
Yes. So I look at so your spam filter, does it work by spam and signal and noise ratio, like spam and metadata ratio?
Yeah.
Okay. What if an attacker tries to send like 49% spam, 51% valid content?
It's still blacklisted. We actually
We tested exactly
this.
that.
Yeah.
Like 30%, 70%.
The once the spam ratio actually dips below 10%, it passes.
Okay, so
Yeah.
10% spam.
Yeah. So
and
10%. So on average, if you have less than 10% spam, the node will not be blacklisted. But it also depends on how aggressive each local blacklisted each local node filters your content.
Okay. One more question, may I? Okay. Last question. So you said like the two network, the spam and the content network, they
1040,
separate, right?
1040.
They're separate.
Yeah.
So if there's a new node, a new user.
Yeah, because they need time to set up.
Okay, sorry about that.
sorry, please finish, and then we'll have to stop.
Okay, yeah, I'll quick. So there are two networks, right? If there's some new node popping out, how does this new node discover other nodes?
Yeah,
Just like what
we have
Lisa.
hard-coded bootstrap nodes. Like we run it all the time. It's basically that node is one which where the curation model is empty basically. It will just it will not pull content. It will just not do discovery, but it will give you all the nodes it knows right now. So the thing is, this is something you need to entry the network at some point, and we use those bootstrap nodes as entry point.
And so these nodes are still connected to the bootstrap node, so you can discover these small networks through that. And so you can discover which network you want to connect to.
Thank you.
Okay, thank you. We'll have to stop there. Thank you very much.
Thank you.
Project. Thank you. Okay.